Hello, geometry students. I'm Mrs. Applegarth, and we're diving into chapter 12. This is the first section. It's called Tangents to Circles. I know it sounds like a good sitcom. It is super interesting, but anytime we start a new chapter, there's some vocabulary that we need to talk about. Some of it will be familiar. Some of it will, the words seem familiar, but it'll have a different meaning. Welcome to geometry. That always happens. We take words that we use in the regular world and make it our own geometry definitions. All right, so let's go ahead and write these definitions down. A circle is the set of all points. So here's your equidistance from a center. So you start with the center, and then you have these points all around the center, and they're all the same distance. Whatever line you draw from the center to the end, it's going to have the same distance, and that makes up a circle. The radius is that line. It's the distance from the center to the circle. The diameter, whoop, it goes all the way across. And it's the distance all the way across your circle. It is also half, it's double the radius, or the radius is half of the diameter. A chord. It's pronounced chord. The H is silent. It's a segment whose endpoints are on the circle. They start and end on the circle. The diameter is a special form of the chord, just like a square is a special form of a rectangle. A secant is a line that intersects the circle twice. So if you see the chord stops and starts on the circle, the secant goes all the way across, in and out, in and out. And then a tangent. Oh, I love the tangent. The tangent is a lover. The tangent intersects the circle once. It just gives it a quick kiss. So the tangent just gives it a drive-by. And those are all the little pieces of what we call, you guys are looking at me, you're like, was that weird? They're just a circle and a bunch of lines. Come on, why? Well, there's special relationships between these, and they allow us to find lengths. And in fact, any of those, like, movies from the moon launch times and the space race, you will see a lot, like, we've got orbits and tangent lines, and all sorts of these pieces are important to the science of, space travel. So, anywho, we are going to determine whether it's a chord, a secant, a tangent, a diameter, or a radius. So let's look at all these little lines here. AD. Actually, let's get a highlighter. A green highlighter. So AD goes from here to here. It does go through the center, so it gets to be officially called a diameter. CD. Starts at the center and goes to the edge, so, or goes to the circle. So it is a radius, GK. Don't you love how this software just straightens all my lines out? I wish I had software like that for my life. GK goes, it starts from the outside, goes into the circle, and then goes back out again. It is a secant. EG. Oops, I started the wrong way. Psych. EG is outside the circle, gives it a little kiss, and then continues on, that is a tangent. It just touches it once. And then HB, H to B. That one starts on the circle and then ends on the circle, so the endpoints are on the circle. It is a chord. Remember, the H is silent. All right, we're going to look at some ways to relate our tangents. A common tangent is a tangent a line that's tangent to two circles. A line that is tangent to two circles. So it goes and touches, it just grazes this one, and then keeps going, and it grazes the other one. My experience is with engineering, and this looks a lot like a pulley system. If you look in your car, there is like your fan belt, and it goes around pulleys that look almost exactly like this. It is, so when you go, Ms. Howgart, why? Because this is how engines run. We put wheels connected to our drive shafts, and then they turn it, and then the belt pulls. It's so much fun. So for real life. Common internal tangent is a tangent that intersects the segment connecting the two sectors. So first, let's put in a line that goes center to center. Okay, well, close enough. Okay, so here's our line that connects the centers. I don't know why I care so much, but I want it to be really on the center. The tangent intersects the segments connecting to the center. So our tangent, a common internal tangent, is going to look like it's going to swing past our first circle and just touch it and hit our second circle. Like so. Okay, and then a common external tangent doesn't do that. So it just takes, I know you guys are like, Ms. Alvegard, that is so cheating. It just grazes each one and doesn't intersect the interior. So, yeah. Just gives a little grazing on the outside. So common internal tangent and common external tangent. All right. Our point of tangency is where the tangent touches the circle. And there's a couple relationships that happen at this place. If a line is tangent to a circle, then it's perpendicular to the radius drawn at the point of tangency. Let me get my circle going. I don't know why I'm drawn to green today. All right, so here's a circle. If a line is tangent to a circle, so let's get a line that's tangent. Okay. Then it is perpendicular to the radius, so right where it touches, down to the radius. Right at that point, we are perpendicular. Oh, that yellow is not going to work for me. Perpendicular. Okay, so yay, when we have 90-degree angles, we've got Pythagorean theorem, we've got trigonometry. We can figure out other angle relationships knowing that this is 90 degrees, and then use that to find lengths. All right, if a line is perpendicular to the radius of a circle at its endpoint on the circle, then it is tangent. So this is just the converse of theorem 12.1. It is saying, well, if I have If you have a if you know it's perpendicular, then you can say it's a tangent. Or if it's tangent, you know it's going to be perpendicular to the radius. So let's see how we can use those relationships to find stuff. Okay. I want to change and get a pen. All right, so we have some dimensions. We want to see, is EF tangent? Well, if this is 90 degrees, then a squared plus b squared has to equal c squared. So we're going to test, is 11 squared plus 60 squared equal to 61 squared? So we take our little calculator out. Pardon me while it loads. Take this time. All right, so we got 11 squared plus 60 squared. That's 3721. Is that equal to 61 squared? Oh, it is. It is equal. 3721 is equal. And then we can say EF is tangent. All right, we're going to test, is this EF tangent? So if this was 90 degrees, we'd have 5 squared plus 9 squared equals 10 squared. I do not need my calculator for this. I'm going to put a question mark because we are asking, is it equal? So this is 25 plus 81. Is that equal to 100? 25 plus 81 is 106. That is not equal to 100, so EF is not tangent. I know, I'm so sorry for you guys who've been trying to get rid of Pythagorean theorem in your life, but he's still flying pretty strong around here. Theorem 12.3 says if two segments from the same exterior point are tangent to the circle, then they are congruent. And let's see how that goes into effect here. So x squared plus 2 and 11 are these lengths. Because they originate from the same point and are tangent to this circle, using this theorem, they have to be equal. So we go x squared plus 2 has to equal 11. We are going to use some algebra to solve this out. And we get x squared equals 9. We take the square root of both sides, and we get x is equal to 3. Well, in truth, x is equal to positive 3 or negative 3, because negative 3 times negative 3 is also 9. I know, sorry. There's two answers to this one. X is equal to 3 and negative 3. So we're using this property to find, and some algebra to find missing variables. All right, let's look at this example 4. A tangent is drawn to a circle from a point 13 centimeters from the center of the circle. Oh, you know I'm a visual learner, and I'm going to need that. Let's get it out of my problem. Okay, so here's the circle. A point 13 centimeters from the center of the circle. Center of the circle. We're going to go, just shoot it straight out. I obviously need a line helper. Let's go line, because I can't draw straight lines. Okay, so this is going to be 13. Our radius is going to be 5. What is the length of the tangent? should draw this so that it looks like what it's supposed to be. Okay. So we're the tangent line is going to be it's going to go past the circle. It's going to hit our 13. We know that this has to be a 90-degree angle. This is 5, this is 13, and then this is our tangent. Okay, I'm going to say it's t for tangent. T squared plus 5 squared is 13 squared. T squared plus 25 is 169 minus 25 minus 25. T squared equals 144. Take the square root, and t is equal to 12. But Miss Applegarth, why is this guy plus or minus 3 and this guy is just 12? Well, here we're solving for a variable and not a distance. Distances are always positive. Even when you walk backwards, you are walking a positive distance backwards. So when you're talking distance, it's asking what is the length of the tangent. Lengths and distances are always positive, so we know that it's going to be positive 12. Okay. Example 5. In the circle, what is the value to the nearest 10th? All right, so we know that this is the radius. We know that this is tangent. From here to here is 10. Here to here is 7. We want to find x. So let me show you how we put this together. We're going to look at total distances. A squared plus b squared equals c squared. So A is x, B is 10, C, and I'm using Clarion theorem, C is 7 plus x. And if you'll allow me to write it as x plus 7, I like the variables in the front. All right, so we get x squared plus 100 equals, we're going to multiply this out. If you don't know, I'll do it the long way here. We're going to encounter these a couple more times in this section. There's a quick and easy way to, when you have binomials that are squared, to get the answer. And I will share with you how I do that without, right now I'm using the FOIL method, but without using the FOIL method. So when I have a perfect square, I take the first one and I square it, and I'm trying to just distribute it out. I take the second one, combine it with the first one, and double the number on the front. So this would be 7x, and we put them together, and I'm just going to double it. And then the last one, just take the last one and square it. Or if you're more comfortable just multiplying it out, just multiply it out. Whatever way you want to get to the end result is fine with me. Okay, I'm going to throw, let's subtract the x squareds from both sides. Remember, if it has an exponent on it, it can only combine with stuff that has the same exponents. So this x squared can only combine with another x squared when you're adding or subtracting. It is quite convenient that the x squareds cancel out. Thank goodness, it would have been a bit of a mess the other way. Okay, we subtract 49 from both sides, so now I have 14x on the left side and 100 minus 49 on the right. We get 51. We divide both sides by 14. And x is equal to 3.6 centimeters. Yay! Algebra! I love algebra, you guys. So rad. Okay. All right, you guys go take a moment, complete the practice problems assigned to you from this section, and then hop back here to check your answers. So the answers to the last problems are first, and the answers to the first problems are last. Okay. Let me know if you need any help with anything, and have an amazing day.